Hello guys, today we are going to discuss DC biasing. In a DC biasing we are going to discuss fixed bias configuration. So here in this circuit we are going to find the following terms, and then we will discuss the DC biasing as well with the calculation. So in the first case what we are going to find, now in the first case we are going to find IBQ and ICQ. In the second we are going to find VCE, and the third we are going to find VB and VC. In the fourth case we are going to find VBC. So let's start with the first case. For the first case we are going to consider the forward bias of this transistor. So the base and emitter are actually the forward bias of this circuit. So let's consider the forward bias, and then we are going to apply voltage Kirchhoff law. Now this is the forward bias of this circuit. So for finding IB we are going to apply Kirchhoff voltage law. So according to Kirchhoff voltage law, VCC, which is the voltage here, minus VBE, which is the voltage from base to emitter, is equal to the voltage drop across the resistor RB. Now so this is the equation. From this equation we can easily find IB, and for IC what we are going to do, for IC we are going to use this equation. So let's put all the value here in this equation. Now for finding IB, VCC here is a 12 volt minus VBE is actually 0.7 volt divided by RB, which is 240 kilo ohm. So if we put all the value here in this circuit, in this equation, so our final result will look like this. So IB is actually equal to 47.08 micro ampere. So let's put the calculated value here. So we got IB, which is equal to 47.08 micro ampere. So .08 micro ampere. For IC what we are going to do, we use this equation. Now so here this beta K is given here in this circuit, which is 50 cross 47.08 micro ampere. So if we calculate all these values, so IC is equal to 2.35 milliampere. So the calculated value here is 2.35 milliampere. Now to find VCE, what we are going to do, we are going to consider that part of the circuit. Let's consider now. So to consider that part of the circuit, what we are going to do, we are going to apply voltage, Kirchhoff voltage law. So voltage source here is VCC minus VCE is equal to ICRC. Now VCE is equal to VCC minus ICRC. So VCE can be found from this equation. So let's put all the value. So to find VCE, what we are going to do, we put the value of VCC, which is 12 volt minus IC, which we found here is a 2.35 milliampere, and RC, which is 2.2 kilo ohm. So if we calculate all these value, what we are going to get, we got 6.83 volt. So VC is actually equal to 6.83 volt. Now B case can be written here. So let's write B case, which is VCE equal to 6.83 volt. Now to find VB and VC in the third case, what we are going to do, so as we know that VBE is actually equal to VB minus VE. So as we know that VE is grounded, so it's equal to 0. So here VB is equal to VBE is equal to VB, which is actually 0.7 volt, and VCE is actually equal to VC minus VE. So as we know that VE is actually equal to 0. So VCE is actually equal to VC, and that is equal to 6.83 volt. Now the calculated value in the third case we put here. So let's put some partition and put all the value here. So IB, IC, so IB is equal to 4.47.08 microampere. IC is equal to 2.35 milliampere. Now VCE is actually equal to 66.83 volt. Now, so this is B case, this is A case, and the C case. VB is equal to 0.7 volt. VC is actually equal to 6.83 volt. Now, so to find VBC and the fourth case, which is the D case, what we are going to do, so VBC is actually equal to VB minus VC. So VBC is voltage from B to C. So here VB is actually 0.7 volt minus VC here is 6.83 volt. So we got VBC is actually equal to minus 6.13 volt. So this is actually a PAX biasing configuration. So our final value VBC, we have found that value. So that's the end of our lecture. Thank you for watching. See you in the next video.